So we have 6 main type of properties: the unit test, valid state, variable transition, state transition, high-level properties, and risk assessment properties. It's a way that I like to split properties, but it's not a clear cut. So a property can be even more than one category. And our goal is actually to get into a good coverage, okay? And it's not necessarily that there is one property that will detect a particular bug. It can be multiple things that we can write that will actually give us the same coverage. So if we can think about it as this is the screen here. So if I have my whole set of states that I want to cover, then I can have a few unit test rules. And they are not necessarily distinct, meaning that they can have some overlapping relationship. And then I can have additional valid state rule that might also cover something that is already covered, but they probably will cover more. And I can have my high level and my state transition covering a little bit more, and another valid state. And my goal is to get as much as possible coverage. So I do say that the high level, the valid stage have much better coverage than unit test, but as I explained here in the graph, some things can actually only be checked with a unit test rule, okay? So it's not one instead of the other. And it's a little bit of a task just even thinking about the properties and designing them. Okay, so unit tests, as they sound, they are usually checking one method per rule. We want to describe the expected output. We want to describe the expected state change from this function, and we can also reason about the reverting condition. So this is the type of rule that we have seen many times. We have something before, we have something after, and we want to check that the after makes sense as a function of what we had before. Okay. Now, one of the dangers in unit test is that we sometimes just copy the original code. Okay. So if you have a bug in your original code and you just copy the same bug to the unit test, the verification will say all good, right? So we have to be very careful, and we actually want to look at the function, but not look at the implementation. Okay, so I will look, for example, here is a real function from OpenC Seaport that it's an internal function, okay? But I want to check it. And I look at the arguments and I see, okay, it should revert on invalid or return a valid indication if the order is valid. So this is a rule that actually finds a bug in this function. And the idea is that just looking at this interface, I can say that if the revert on invalid is false, it should never revert, right? Because that's exactly what it's supposed to do. Well, actually, it does revert, okay? So this is a nice rule, and it's without looking at the exact implementation, just from looking at the definition of the function. So these are nice. This is a very nice unit test rule. Another nice unit test rule will be to compare different runs, okay? So here we say we still have this verify order status. If we call it with true, and we call with the same arguments again with false, so if it reverted on the first case, right, then it should have been false on the other case, right? Makes sense? Okay, this is a very, again, this is a very strong unit test tool. It doesn't look at the exact implementation. It looks at the arguments and the return value of the function. Okay, so these are comparing different ones. We even have a technology for comparing different ones on state changing functions. Okay, it's a little bit more complicated because once you change the state, you need to go back to the original state, but we have this feature in CVL. So comparing different ones is very, very strong. Okay, so these are the unit test rules. So as we said, don't copy the original code. Try even not to look at the implementation. The idea is that you learn, you might sometimes need to look at the implementation just to understand, because some code doesn't have very good documentation. So understand what the function is supposed to do, forget the implementation, and write your rules. Okay. Our next type of properties are, any questions on unit testings before we will move on? Okay. The next type of properties is what we call valid states. Those are the very strong invariants, variable relationships that we also had Muli discuss when talking about induction and invariants. They are expressions over the system variable that should always hold. Okay. Again, we want to identify groups of related variables. And we should think about things that should never happen. What should always hold, and if it breaks, it can indicate of a real problems. Again, I would like to do this by looking at the data structure of the program. Okay, this is from compound, compound v3 called comment. It has for each user. So compound, I believe everyone knows, it's a lending protocol. Someone can be a liquidity provider and provide collateral and then can borrow. So there's for every user, for every token, for every user, there is the amount of collateral he gave to the system. In addition, for efficiency, there is a flag, there is a bit representation of which asset are collateral for a specific user. So just from looking at this definition of the contract and the states, I can think about like, okay, so if this flag is true, there should be collateral, right? So, and this is exactly a valid state, right? It shouldn't be that the user has zero balance in some token, but the flag is turned on. And probably more problematic is that if the flag is false and a user did provide collateral, that means that this collateral will not be taken into account. And this is exactly a bug that we have found. Again, during early development state, we were working with compound. And this is a very strong rule, okay? So we say that if the user collateral balance on a specific asset is greater than 0, now we have the double implication. If and only if the is in asset flag of the index of this asset for this user is turned on, okay? Right, so the double implication is if and only if. Either both are true or both are false. Okay, so those are the valid state. Usually valid states are written as invariants, but not necessarily. Sometimes they are written as rules, but most probably it is an invariant, and it is an inductive invariant that should always hold. Okay. Next set of properties is what we call variable transition. We want to reason about a specific variable. We can actually sometimes rewrite rules that reason about many of them, but the idea is that we look at changes that happens to the variables. And we ask when can something change, meaning like which function can change it. So if I have here this parametric rule, change delegation, I have the delegation before, the delegation after. I call this on every function. We all, anyone needs to remind about parametric rules? We went over this yesterday. I'll just say one the small description of this. We actually check this rule on every method that is external or public in the Solidity contract. Okay. So if it changed, then it implies that it's one of the functions that are allowed to change this. Okay. So this is one type of reasoning about changes to a variable. And then we can also ask, but who can change? Maybe we don't really care. Many functions can change, but it should be a specific message sender. Okay. So this is like only a user can change its delegatee. Okay. So, and then we can also ask ourselves, what change is valid? Can it only increase? Can it only decrease? Is it under some kind of a condition that it might change? So here is an example of a rule that we actually check the balance in some token, arbitrary token is free, of the current contract. Okay, current contract is the contract under a test, the main Solidity contract we are analyzing. And we say that if the balance change, we want to make sure that this token has been a registered token to the system. So this is actually a rule that can make sure that no malicious token has been crafted to get into the system. Okay, so it actually, in a very simple rule, we actually check that the system only use valid tokens that have been registered. Okay, think about writing this as a unit test. You have to check every function. Okay. All right. Okay. And so this is what can change, under what conditions. Sometimes we will see that, okay, if it can only increase, it can only decrease. And these are probably the most strong variable transition. They actually want to say that if something changed, something else would have happened, or it should change only under some other condition. Okay, so this is an example also that actually found a real bug in one of our customers that were actually, they wrote this rule by themselves. So it's the total deposit to the system and the total supply. So it's like, again, a lending protocol that there is liquidity tokens giving. And they want to say that if the total supply of changed, then it should only be if the deposit, the amount of deposit have changed. And look how simple this rule is. It doesn't even talk about, is it increasing, is it decreasing, right? We can actually make it probably much stronger, but by discussing additional properties. But even a simple rule like this, if it changed, the others should change. I've actually caught a very critical bug where they would have lost all the fees they have collected. Okay. Okay, some do's and don'ts about variable transition. So we have summarized all of this. So we want to reason about the changes, want to reason about when, about who, about what change is valid, and what else would happen to the system if it changed. Okay. We shouldn't do any reasoning about immutable or constant variable. We trust the compiler. We check the compiler, but we also trust it. And we shouldn't reason about view functions. They don't change anything. So we can filter them out in this type of rules. I don't want to see rules like with, okay, this function, it's okay, this function, it's okay, and it's all view function. We can just filter out all view functions in one step. Okay, so those are the variable transition. Next are the state transition. So sometimes a nice way to think about the system is to think about the system as a state machine, as an automata, like we probably learned in high school, university. And we can define a different state. It can be for the whole system. It can be for a particular user of the system. It can be according to some kind of ID. I don't know if there's like a claim ID, something like that. What is the status of this asset, this thing in the system? So this is, for example, for a lending protocol. We can say that it starts from a user starts from the empty state. If it deposits, he becomes a liquidity provider. If it would withdraw, then back to the empty state, that it's not a user of the system. But if he borrows, he should be in a state that it should be always collateralized. And additional borrowing or deposit should live. The user should stay in the collateral. And if he repays everything, he comes back to being a liquidity provider, and then he can withdraw. So this actually defines all the valid transition of the system. Anything that is out of this should be invalid. So one should not be able to be at the empty state and borrow. One should not be able to borrow and move out of the collateralized state, being uncollateralized. So this is also a very strong way to think about the system. And then we can define in a rule valid changes. Okay, so here we have an example. We just define like a state, right? I don't know, this is for like meetings or something like that, but we can think about it about anything. And we check the change. So if before we were at the specific state, then we should either either stay at this state or move to another state. And we can also reason about, okay, if I was before that specific state, I move to another state, which functions are valid? So it's a combination of what we have seen before on the variable change transition, but these are not on a specific variable. It's like on a state, on something that is a little bit more abstract. Okay, this get state by ID can be something that is actually computed like a view function. Okay, the next state set of properties are what we call high-level properties. They usually cover more than one part of the method. They can reason about fundamental parts of the system. So like the total amounts, the total shares, those are things that we can easily write in our language. We can also refer to external contract. So I can ask how much asset does the system actually hold in another token, in another contract. So this is for an example, like the total supply should be less or equal to some kind of an underlying token, the balance of the system, the current contract. Okay, so this will be high-level property, but you can also think about it as a valid state, right? It's an invariant, it's over variables, connecting to variables. So again, it's not that clear-cut, but definitely it's a high-level property, meaning that if this breaks, something is wrong with the system. It doesn't hold as much as assets as it should hold. Okay. And the last type of properties are risk analysis. So this is like thinking about what would be an attack of the system? What would be devastating? What should never happen? Those are kind of thinking you have to like put your other hat on, put your black hat on, and think malicious, okay? Think that you want to break the system, and then you can think about those properties. So if I can withdraw twice, if I withdraw all my balance off, if I can draw all of them, right, I shouldn't be able to withdraw again, okay? So this is like no double withdraw. If I can withdraw anything, even one, after I withdraw all my amount, something is wrong, right? Someone will use this this option to withdraw more than it holds. Okay, so those are the risk analysis. Again, the nice thing is that we can define them with symbolic values. Usually it doesn't require very, very complicated rules. It does require thinking about those properties. So what I would like to do now is to have an exercise, and we can go over a liquidity pool. Anyone? So there are three main functions. There is deposit, where you deposit some amount of an underlying token, and it gives you back liquidity shares token. So this is like, for example, like becoming a LP provider. So it means our liquidity pool is by itself an ERC20. This is a little bit like the example we have seen yesterday, I think. And then we can withdraw, wait, one thing. And then there is withdraw. So when you withdraw, you give back your liquidity tokens and you get back your underlying token. The last function is a flash loan. Who is familiar with the flash loan idea? Okay, so I will describe for those that are not. So flash loan is a very powerful feature that DeFi applications provide. The idea is that an external user in one transaction can come take a loan. It doesn't need to be backed up by any collateral, but it has to be in one transaction. He has a callback where he can do whatever he wants to do with this amount of token that he has taken. But at the end of the transaction, he has to give back everything that he's taken and pay a fee. Okay, so it's one transaction, meaning that if the user didn't pay back the flash loan, then there will be a revert of all the transaction that he has done. Okay, so this is one way that actually liquidity providers obtain fee. Okay, so the fee is supposed and hopefully is split between the different liquidity providers according to their shares. So the more shares I have, the more fee I should get, right? Okay, so we have in our tutorials that this is the tutorial branch. You do need to pull if you already pulled it. We have, I think it's not under day 2. It's just under symbolic pool, liquidity pool. And what I want you first of all to do is just think and plan properties. I opened a document. We can just update there. Let me go first of all to the code. So it's the liquidity pool contract. So it has the deposit function, okay, for depositing an amount, and it returns the amount of shares that one is receiving. Withdraw, it's like the opposite. And there is the flash loan function. Okay, so this is exactly the callback that we discussed. Okay, so one can receive from the system an amount that you desire, and then there should be the flash loan receiver, the call to a flash loan receiver, and we have here a symbolic flash loan receiver. We already implemented this, so this is also a nice feature that we have in our, because we are working very symbolic, we can just simulate in Solidity many different executions. So here our flash loan receiver, what? Oh, it's not sharing everything? Sorry, I was thinking I was sharing. How do I do this? Okay, should I? Yeah, now it looks better, right? Okay, back. Sorry. So we have the liquidity pool contract. Okay, it basically has three main functions: the deposit, the withdraw, the flash loan. And these are the functions that we actually should write properties. We can also write properties on the calc of the fees, or a computation of shares to amount to shares. And the idea is, first of all, to plan. So, and there is here in the pool spec, there is some start, but I want first of all to plan. So you also have the link. Is it opening? You also have a link to a shared document, and we can just write here. You can just add your ideas. Or if you want, like, add a different section, if you want to do only your ideas without combining with others' ideas. And the idea is that we will review this together. So, yeah, let's do this. Okay, any questions first of all? Okay. Yeah, so okay. Yeah, so let's take about like 20-30 minutes to go over the contract. Again, don't look too much and just design, just write your properties in English, and then we can, I would like to discuss it. And this will be the contract that we will be working on today. We will write rules for this contract, and later on we will learn how to check the spec. This will be our noon lecture, where we will actually, we discussed this yesterday, that it's kind of tricky to get the rules right, and we have actually tools and methodology to make sure that our rules are good. Okay, thanks.